Now to discuss the geology of the landing site in a little more detail is Dr. Malin.
Thank you, Jim.
We're going to take a quick local cable break. Be back with more live pictures coming down from Mars as analyzed by the scientists at the Jet Propulsion Lab. Stay with CNN. We'll be right back. Well, the project scientists thought before they landed here they were landing in a floodplain from thousands of years ago. They have more evidence that they're right. Mike Malin, one of the project scientists, is explaining that now.
Amplitude of these depressions and ridges, in fact, they're mostly ridges that are constructed by deposition of debris. The amplitude is about 4 meters, and the separation of these ridges is about 20 meters. I have not yet been able to measure their length. I just have a few pictures I've had a chance to look at. But this is one piece of evidence that there was a lot of water flowing through here. And the amplitude and the spacing and eventually the length of these grooves and ridges are very indicative of the thickness of the water, the depth of water that was flowing over the surface, and the velocity with which it was flowing. Now the next slide shows rocks you've seen before. The important thing to see here are that these rocks are sort of stacked up against each other. And the direction, the orientation of that is 20 degrees west of south. That's the direction from which the water was flowing. And for some reason, a boulder, probably this one, stopped moving, typically because the water level was receding and it was unable to move the boulder. And then a series of boulders banged up in back of it, sort of like in Fantasia when the dancing mushrooms sort of stopped short and all the mushrooms backed up in front of it, or the Keystone Cops or something of that nature. And so you have a series of 4 or 5 boulders that bang up next to each other, and we call this the orientation imbrication, or the process or the appearance of this imbrication. And the orientation and the angle with which these rocks are laid down is indicative of the direction and the force with which the boulders were being pushed. The size of these boulders is very sensitive to the velocity of the water, or the fluid, but I think it was water here, and the depth, and to some extent how much other sediment was being carried along by the water. If there's a lot of sediment, many of you have seen mud flows, you can carry bigger rocks because the water and dirt is denser and can pick it up more easily. And if it's clear water, like in a mountain brook or stream, you don't carry much material and you can only move the finest particles on occasion. In this case, these boulders are of the order of 1 meter across, and that's typical of what we call late stage or waning flow processes in a flood. The next slide. Change scale. The water is gone, but it's left behind in irregularities, puddles. What happens to those puddles? They evaporate. And while they evaporate, they concentrate salts and other materials that were dissolved in the water to begin with. And what we see here, as we had seen at the Viking 1 and 2 landing sites, is our first evidence of a crust that was formed by the deposition of these salts and small particles of silica clay materials. This particular one has probably been cracked, you see this fracture here, by the retraction of the airbag. But this is a unit that is relatively rigid. It's friable. You could break it with your hand fairly easily. It's only a few millimeters thick. And we see these in places, for example, in Hawaii, where after a volcanic eruption has laid down ash deposits, moisture within the ash will percolate through the ash and cause a cement to form at the surface and crust the rock. And any of you who've been to the Big Island of Hawaii and walked around on Kilauea have probably found these underfoot. You can see some small knobs or bits and pieces of gravel embedded in this crust. That's also indicative of how the process formed, how the water evaporated and solidified and cemented the rocks together. The next slide, which I think is my last one, shows an area a little bit more to the north or clockwise around the spacecraft from the rock I just showed you, and shows the edge, another edge of this deposit of crust materials that has been exhumed. It's being eroded away and uncovered by presumably wind processes. These scratches down here are again where the airbag was pulled across the surface. And there are a number of other very interesting features within this area that have nothing to do with water, and so I'll just mention them and then pass the baton. One of the things you often find in deserts are pebble strings, where there's a whole series of pebbles that are oriented one after the other, and it looks like something sort of raked them into that pattern. The process by which this happens on Earth is not well understood, but we believe it has something to do with how sand, as it moves through an area, kicks up dirt where it's not protected by stones and does not reach the dirt that is protected by stones. And so if the winds are blowing from a certain direction, you'll get strings of protected areas, which are where these pebbles are, and if the wind blows from other directions, you move the sand out of the way. There are a large number of other geological features, some pertaining to the water that went through the area, some pertaining to the impact crater, which is nearby, and some pertaining to the wind processes that have modified this site over the last several billion years. Hopefully over the next several weeks, we will be able to share with you some of those other stories that we're developing. Frank?
Okay. During the presentation, the team has been joined by two additional scientists, Dr. Julio Megoyes.
We're taking a quick break. We'll come back with the answers to these and other questions. I'll listen in while we pay a couple of bills. Stay with CNN. Our journey to the Red Planet continues in just a minute. Stay with us. Welcome back. Do you care about the atmospheric density about a mile above the surface of Mars? Some people who are asking questions in the news conference right now do care about that. I want to show you the new pictures again real quickly if I can. Let's look at them. This was the first picture ever taken of the mothership by the rover, which proved to them that the cameras on the rover were working well. That's one of those airbags that helped get this thing on Mars without doing any damage to it. It was illustrated by mission scientist Matthew Golombek, who was very excited. Over there, he's pointing to the sniffer device at the end of the rover, which is right now pointed up against a rock on the surface of Mars, known in the trade as Barnacle Bill. On at the bottom of your screen, you can see the tracks made by the rover as it rolled off the lander and positioned itself to do the spectral analysis of the first rock ever spectrally analyzed on the surface of Mars, at least as far as we know. And this is the money shot. The rover's on your right. The spectral analyzer is the thing that the red arrow is pointing to now. It sort of looks like a tomato soup can, and it is pushed up against that rock, and its sensors are getting whatever information that rock can tell us about what it's made of. It's being sucked back into the rover, and the data from those instruments and the computer on board going back down to planet Earth. So those were the first three pictures we have seen today that are new of the surface of Mars. There's some other ones in there as well. The briefing is continuing, and I see the Mars weather report on our screen right now. Flip Spiceland was very interested in this, and let's listen and say that it's 76 below zero right now, according to this this update. Let's listen.
Say that the weather today is exactly the same as the weather yesterday. This technique in many parts of the world has a very high success rate. And as you can see, we expect to see a high of about 261 Kelvin, plus 10 degrees Fahrenheit, and a minimum of minus 105 Fahrenheit, 197 Kelvin. The next slide shows the pressure cycle that we measured. This is a by now familiar squiggly curve. As an aside, I'm glad to see the camera team are following our lead in squiggly lines. The red dots here are our data. The blue line is the Viking 1 lander data. You can see we have a complete day's coverage virtually between the middle of Sol 1 and the middle of the middle of Sol 2 and the middle of Sol 3. The pressure cycle on Mars has what we call a semi-diurnal nature at this time, which is to say 2 maxima and 2 minima per day. This is rather like the ocean tides in many parts of the Earth. This is driven by heating in the atmosphere, and this is a rather preliminary conclusion, but one of the requirements to make the tide look like this is that there has to be a moderate amount of dust in the atmosphere, of order 0.5 opacity. It has to be globally distributed in order to drive this semi-diurnal tide, and it has to be vertically extensively distributed as well, from at least up to 40 kilometers. In order to get this type of tidal amplitude, you have to have widely spread dust in the atmosphere. We seem to be a little lower, maybe 1% lower than Viking. We still have a few little calibration issues to sort out. There may be something there, but this difference in pressure is also consistent with the difference in height between us and Viking, which is maybe of order 100 meters. That's about the error bar, 50 to 100 meters in height. And that's enough to give a 1% pressure difference. So we're not at all disturbed by that little offset between the Viking curve and the Pathfinder curve. You can also see the much greater resolution we have into these waveforms, and we're really looking forward to following this as the days progress. We'll get another complete day down this afternoon. The next view graph shows the temperature cycle we see. As you can see straight away, the temperatures are higher at this landing site, both day and night, than they are for Viking 1. The other thing that's worth noting is I've shown the 3 masts, the top, the middle, the lower mast thermocouples, and during the day at the temperature peak, you can see that the top mast thermocouple is coldest, represented by I think it's a blue triangle on top. And the bottom mast thermocouple is the coldest, is the warmest, heated by the ground. As the sun sets, and the ground cools down, this behavior reverses, and the top mast becomes warmest, the bottom mast becomes coldest. And as the sun rises again in the morning, the pattern reverses yet again. What happens during the night, the ground cools, the atmosphere becomes very stable and cool near the ground. We have a strong gradient with the colder sensor nearer the ground. As the sun rises, starts heating the ground, this inversion, as we call it, in the boundary layer breaks up, and the air starts to heat and rise again on the surface and generate and revert to the warmer temperatures lower down, the cooler temperatures higher up in this lowest meter. The final view graph shows the wind data. It looks like a chaotic mass, but if you focus on the period of time about a third of the way into Sol 2, this is the sort of the first third of Sol 2, the night time, we have a very consistent series of wind directions in coming out of the south to southeast, which are the directions of these major canyons. At other times of day, the winds tend to fluctuate both in speed and direction. As you can see, our little red circles are scattered around during the afternoon in Sol 2 and the afternoon in Sol 1 also. With that, I'll bring my discussion to the end. One of the main features of our landed data is that we just wish to keep accumulating data like this to see how this will not be the same day by day, although I gave that impression at the beginning. We will have variations. We expect to see interesting weather features moving through in both the temperature and the pressure cycles. And if we have the luck to survive for months, we'll be moving into a time of year when the pressure is increasing steadily as the South Polar region evaporates, and we see a lot more wind as the dust storm season starts to approach. Thank you.
Okay, we're going to go to questions in a couple of minutes, but first we had
Going to take another quick break. I'll monitor. We'll come back and let you hear more.